Okay, here I'm going to look at a diesel cycle. Okay, compression ratio 17 has an initial conditions like that. The maximum temperature is 4,000, which is state 3. And we're going to do this using the very stupid cold air standard analysis, where I assume a specific heat at 520, which it is not. It's changing from 520 up to 4,000. Specifically, heat is not constant, but that's the assumption we're going to make because it says right here. And so I can show you how to do a cold air standard analysis, even though I don't like it. Okay, so for that, with that aside, we're going to go ahead and we're going to look up my specific heat for 520. So I go to this table right here. This is specific heat. I'm looking at air, and I'm looking, well, I don't have 520, I have 500, but I have CP, CV, and K right there. Okay, so oh, and that's for, I'm sorry, that is for Fahrenheit. So I actually am not 500 Fahrenheit, 500 Rankine. So I'm actually down in here a little bit. So 0.24, 0.17, 1.4. Those are my values there. So I'm going to use CV equals 0.171, CP equals 0.24, and K, the specific heat ratio, 1.401. And again, that is the specific heats for air at 520 degrees. Okay. Now, the idea of setting the states here is to find my temperatures, because then I just use specific heat times the change in temperature. So I already know two states, here and here. So I'm just going to move on to find state 2. And state 2 can be used using this equation right here that was defined previously. Okay, where it's the temperature ratio equals the volume ratio to the K minus 1. And again, I know this is my compression ratio, excuse me. Okay, K is right there, so from this I can calculate T2, okay, to be 1619.6 degrees Rankine. So in there I have set state 2. And that's all I really need to do here. Okay, is the temperature. That sets my states. I'm going to go to state 4 now. Okay, and by definition for the temperature ratio, T3 to T4, okay, it's going to be V3 over V4 to the K minus 1. Okay, just like what I had up here, because again, this is an isentropic process, okay, with a constant specific heat. Okay, but V3 over V4, I don't really know. So what I actually do here is instead of V3 over V4, I take V2 over V4 and V3 over V2. So I just multiply and divide V2 and V3. Okay, now V4 is V1, right? Because the last process is constant volume from 4 to 1, so V4 equals V1. This is my compression ratio of the 17. Well, it's 1 over the compression ratio, actually. Okay, and then V3 over V2, okay, this is the constant pressure process, right? So PV equals RT for an ideal gas. Well, if I take PV over PV, the P's cancel, and that equals RT over RT, 2, 3, and 2. R's cancel, so essentially V3 over V2 actually equals, okay, so this will go VT over V1. This actually equals T3 over T2. So again, I've got my compression ratio here. I know my temperatures, 2 and 3. I know this temperature. From this, I can calculate T4, and I find T4 to equal 1845.5 degrees Rankine. Now I have my states set here. Okay. Now, to calculate the work of the cycle, first I need to find the mass of the cycle. Okay, because again, these are all in specific terms. So I can easily find the mass just because I know state 1. I can use P1 V1 over R T1, and again, I know everything here. So I can actually calculate my mass, and my mass comes out to be 0.1454 pounds mass. Okay, so now I know my mass. Okay, so now that I know that, to find the work of the cycle, the way I'm actually going to do this, I'm going to say work of the cycle equals Q of the cycle. Okay, so that's Q in minus Q out, so that's going to be Q2 to 3 minus Q4 to 1. And I'm going to do that because, again, the work occurs over set. I've got compression, and then I've got work here, and I have work on the expansion as well. So it's just easier to do it in terms of Q. Okay, but you'll remember Q2 to 3, that's the constant pressure, right? That's where the H, delta H comes in. So I actually am going to use CP for that one. Okay, so I'm going to take mass times all of this, and then it's going to be CP times delta T for 2 to 3. Okay, and again, that's because of the constant pressure process that I've got going on. So I'm using delta H, which is related to CP, minus the heat rejection during the constant volume process. So that's just delta U, so that's going to be CV delta T. Okay, so the work of the cycle then is 50.11 BTUs. Okay, again, work of the cycle is the same as Q of the cycle. Q in is delta H, which is CP delta T for this stupid analysis of constant specific heat. Q out is delta U, which is CV delta T. Okay, and that gives me the work of the cycle. Now that I have the work of the cycle, I can find the efficiency, which again is that work of the cycle, over Q2 to 3, which is CP delta T. So I just throw that in there, and I can find that the efficiency is actually 60.3%. Okay, so again, this uses the very poor assumption that specific heat is constant. Okay, my preferred method would be to use the tables, look up U and H values as necessary. But again, this is just to show you how to do that cold air standard analysis a little bit easier, just calculating temperatures using specific heats and compression ratios and things like that as shown here.